All right, so Chapter 5, Section 9 is building exponential, logarithmic, and logistic models from data. So we're going to have a table of values, put them into our graphing utility. My recommendation is you use a graphing calculator because of the variety of logistics models that we're using. It's just a little bit more streamlined to do it on the graphing calculator than it is to try to find the different types of models on the computer. So what we're going to be doing is we're going to be looking at data, plotting it on a graph, and then trying to match it to either exponential. So remember when your b is greater than, your a and b are greater than 0, your exponential function has a nice curve upward. And when your b is between 0 and 1, your exponential function has a downward curve. The logarithmic function, y equals a plus b natural log of x, when a is greater than 0 and b is less than 0, it has a downward curve. And just to make a little note, different than the downward curve from exponential. And then the classic logarithmic function comes up from x equals 0 up and curves around. Those are logarithmics. The logistics model, remember with the A, B, and C, he kind of looks a little bit like this, which this doesn't look anything like, it kind of looks like that sideways cubic function. So what we're going to do is we're going to take those data types and find the logistics model that most closely matches so that we can use those equations to predict. All right, so we got Kathleen. She wants to explain the growth of cell phone usage in the United States. She gets tons of data from 85 to 2005, and the data is on the next slide. We're going to draw a scatter diagram, find an exponential function fit to the data, write the formula, graph that formula, and then use that formula to predict in 2009, and then talk about the k value that we get from our data. All right, so here's all of our data. We're going to let 1985 equal 1. So we're just putting in, anytime you can switch the years to, instead of 2004 to just a singular number, it makes the data a little bit easier. All right, so you put all this data into your graphing utility, and then you look at the scatter plot. So to me, they want us to model an exponential function. So you go to your stat, you find exponential regression, and you do exponential regression from list 1 and list 2. It'll give you A and B, and A is the coefficient and B is the base. So then you put those numbers in to have a nice little exponential equation. And remember, the closer R is to 1, the more nicely the data fits the model. All right, so we write it as a sub 0 e to the kt. We're going to let x equal t. And when x is equal to t, which is equal to 0, we find that a is equal to a sub 0. So if a is equal to a sub 0, bx is equal to e to the kt. So if we raise e to the k to the t power, then we see that bx equals e to the kt. And we just look at the bases here. Base b is equal to base ek. since x is equal to t. So to write it as this function up here, we find that a sub 0 is equal to 0.86498, b is equal to e to the kt, which is equal to 1.31855. So since e to the k is equal to 1.31855, we need to find k. Because do you see what's happening here? We're trying to get base e into our equation. So we're trying to be a little trixies on that. So when we get to the e, we take the natural log of both sides, and we get k equals natural log of 1.31855. Which is 0.2765. So we're going to go back, plug everything in here. A sub 0 is this. K is 0.2765. So our function is 0.86498 e to the 0.2765t. So when we put that, we compare that function to our logistics model. It's not too bad. And then we're going to let t equal 25, which is where we are at 2009. And when we plug in 25 to our function, we get 869, which is millions. And that's our prediction. The value of k, 0.2765, represents the growth rate of the number of cell phone subscribers in the United States. Over the period from 1985 to 2008, the number of cell phone subscribers grew at a rate of 27.65%, compounded continuously. This growth rate is not sustainable, as we learned in Part E. If you're asked, in problem 10, you were asked to build a better model from these data. Okay. So now we're going to look at the logarithmic, that was exponential model. This is logarithmic model. So we got a meteorologist wants to find the relation between the height of a weather balloon and atmospheric pressure. And she collects data. We're going to do the same thing as we did before. Graph the scatter diagram. Find the function of best fit. Draw that function and compare it to the scatter diagram, and then use it to predict 560 millimeters of mercury. Okay, so here's our data. Here's a scatter plot that follows. We're going to use the logarithmic regression, and this is natural log regression. It's we look at our r, and it's pretty close to 1, so it matches pretty nicely. We go ahead and put this equation into our graphing utility and put it on the same graph as our scatter plot. And then we use that equation to find when what's the height at 560 atmospheric pressure. Calculator chug. 2,108 kilometers. Easy peasy. Okay. Now we got the logistic model. We are going to use the table to represent the amount of yeast biomass in a culture after T hours. We're doing the exact same thing as we were before, except we have the carrying capacity in this calculation. Okay, so here's our data. When we put it in, it looks pretty logistics model-y-ish. It's got that sideways swimmer look to it. So we find the logistics calculator, and it chugs out A, B, and C for us. If you don't know how to find any of these, a quick way to find stuff is in the catalog. Go to the catalog. Alpha automatically engages when you're in your calculator catalog, and you just press the L button, and it will take you to the L's, and you scroll down and find logistic. You graph that equation on the same graph as your scatter plot. And then we are going to plug in we know that the carrying capacity is the same as the top number in our equation. It's the same value as the C value. We want to know after 19 hours what our function is. And so we plug 19 in and we get 661.5. And that's it, guys. Woo! End of chapter 5. We did it. We made it through.